class, welcome back to multivariable calculus. In this lesson, we are going to learn about parameterized curves. And the key here is the term parameter. And so our parameter in this case is going to be time. So we're going to look at curves, so position, as a function of time. So essentially, we are going to be drawing these curves or tracing them over time. And so let us begin with an example looking at the sine and cosine functions. And what we're going to do is it's really important when working with parameterized curves to always set your time interval. And so let's set our time interval for this example to be 0 is less than or equal to t is less than or equal to 2 pi. So for our first example, we are going to look at the following. We're going to look at x is equal to cosine t, and y is equal to sine t. And we all know that this is going to give us in the xy plane a circle, but let's just look at the functions over time. All right, so we're going to look at x versus time and y versus time. And if we were keeping track of time below, all right, so beginning at 0, for example, t is 0. All right, our x and y coordinate, so cosine of 0 is 1, and sine of 0 is 0, right? So if we just sketch out the cosine curve and the sine curve over 2 pi, so then if we looked at pi over 2, for example, then cosine of pi over 2 is 0, and sine of pi over 2 is 1. So let's look at this on a y versus x, the xy plane. So y versus x, and this will be 1. So at time of 0, we are starting at 1, 0, because we plug in 0 for t in both cases to get our coordinate. So then at time of pi over 2, we end up with 0, 1. And we can keep going like this. At time of pi, t equals pi, we end up with minus 1, 0. At 3 pi over 2, we end up at 0, minus 1. And so what we're doing, if we were going to draw this pathway out, we'd be drawing the unit circle counterclockwise, starting at 1, 0. So that is our parameterized curve in this case. So let's look at now another example. So what if then x is minus cosine t and y is sine t? So if we looked at that, I'm just going to draw a little smaller down here at y versus x. mark off our ones. So then what's going on here is we are going to be starting at, when you do minus cosine t, that's minus 1, and we still have sine t for y. So we are starting at minus 1 and 0. So we're starting over here. And so then if we tried pi over 2, then what happens if we plug in pi over 2, we end up with 0, 1. And then we can plug in pi and we'll end up with 1, 0, and 3 pi over 2, and we'll end up with minus 1, 0, or 0 minus 1. And so what's happening is we're starting at minus 1, 0, and we're drawing the unit circle clockwise. So that is that parameterized function. Now, let's try it again. Let's do x is cosine t, and y is sine t. Y is minus sine t. So if we were to sketch this one out, so then what's happening is we're going to be starting once again at 1, 0. But then what happens when we go to pi over 2 is we're going to end up at 0 minus 1. So we're starting this time, once again, like our first example, we're starting at 1, 0, but we're going to be drawing our unit circle clockwise. Okay, one more. I bet you can guess what it is. So if we looked at, then x is minus cosine t, and y is minus sine t. Like our second example, we're going to be starting at minus 1, 0. So we're starting at minus 1, 0. But then if we plug in pi over 2, we end up at 0 minus 1. So we're starting at minus 1, 0, and we're drawing our unit circle counterclockwise. All right. So another way you can look at this is if we start with our x equals cosine t and y equals sine t and compare what's going on here, then this second example, we're reflecting our first, so I'm just going to put a little star here. So we're going to reflect over the y-axis to get that. Okay, so taking like a mirror over the y-axis is what gives us this one. It's a mirror image of this one if we've reflected over the y. And for the second one, we're reflecting over the x. And for our last one, we're reflecting over both. So now let's just come up with a standard relation here for a circle of radius r centered at AB. So we're describing a circle using parameterized curves. So for a circle of radius r centered at AB, x is going to be equal to the x coordinate of the center, so A, plus the radius of the circle, r, times cosine t, And y is going to equal b plus r sine t. Okay, so this is how to draw a circle of any radius at any center in the xy plane, for example. So now let's move on to an example using this. So let's give a parametric equation for a circle, or give the parametric equations for a circle of radius 4 parallel to the YZ plane centered at 5, 0, 0. Okay, so here's the thing. It's going to be, our circle is going to be parallel to the YZ plane. And so that's what we want to focus on because we're drawing that circle in the YZ plane, not in the XY plane. And so if you think about it, the center is just up 5 in the X direction. So X as a function of time is just going to be 5. So since we're drawing the circle in the YZ plane, y as a function of time, well, the center coordinate for y is 0, so it's going to be 0 plus the radius times cosine time. So the radius here is 4 cosine t. And z as a function of time, the center of z is 0. So it's centered at 0 for z, and that's going to be 4 sine t. Now you could flip sine and cosine if you wanted to. We're just trying to draw a circle. We're not talking about any specific direction. And since we're drawing a circle, it has to be at least between 0 and 2 pi to draw a full circle. If we're only drawing a half circle, we'd go from 0 to pi. So in vector form, we could write this. So vector r of t. So if you've taken physics, just like in physics, we're looking at a position vector as a function of time. So it's similar syntax here. And so r of t, vector r of t, is going to equal, well, as a function of time, in the x, we're going 5 I hat plus the y is going to be 4 cosine t j hat and z is going to be 4 sine t k hat. Okay, so we're just using the x, the y, and z. Those are going to be the components, the x, y, and z components of our vector. So the I hat, j hat, k hat. Now let's do another one, and I would like you to try this one on your own first. So give a parameterization for a semicircle in the xy plane with x is less than or equal to 0 that begins at 0, 1 and ends at 0, minus 1. So pause it, try it on your own first, and then resume when you're ready to see the solution. So we are in the xy plane. So I'm going to draw out, I'm going to sketch out the situation first. And we're beginning at 0, 1. And we're ending at 0, minus 1. And x is going to stay less than or equal to 0. So we're over here. So we're going that direction. And we have our semicircle. So you can describe this multiple ways. There are a few different correct answers here. But the key is specifying your time interval. Your time interval has to match up with your parameterization. So x, if we say x is sine t, for example, and y is cosine t. All right, so we want to start at 0, 1. Well, let's just say that I'm going to set up a time interval of 0 is less than or equal to t is less than or equal to pi, since we're doing a half circle. So at time of 0, if we wanted to start at 0, 1, then we would have sine of t is 0 for the x, that works. And then cosine of 0 is 1 for the y. Okay, that works out great. So then we want to get over to minus 1, 0 for pi over 2. So if we do x is sine pi over 2, oh wait, that gives us 1. So that would put us over here. So what we're going to have to do here is we're going to have to stick on a minus sign. So x is minus sine of t gives us the minus 1 for our x, and pi over 2, cosine pi over 2 is 0. So that works. And then finally, if we plug in pi, well, sine of pi will give, minus sine of pi will give us 0, and cosine of pi will give us our minus 1. So our parameterization is going to be vector r of t is equal to minus sine t I hat plus cosine t j hat. And of course, you could have kept it with, say, x is cosine of t, y is sine of t, and you could have adjusted to go from pi over 2 to, say, 3 pi over 2, for example. So there are different ways you could have done this. All right, let's keep going. Now we're looking at, let's look at the parametric equations of a line. Okay, let's move beyond the circle and look at a line. And so if we're going through the point, some point, x naught, y naught, z naught, parallel to some a I hat plus b j hat plus c k hat. So here's what you would have for the parametric equations. So x coordinate is going to be equal to x naught plus at, y is going to equal y naught plus bt, and z is going to equal z naught plus ct. All right, so we have, so this is our starting point, this x naught, y naught, z naught. So that's our starting point. And then how far we're moving from that point in time. Okay, and this would be in the x direction. For A would give us the component in the x direction. B would give us the component in the y direction that you're multiplying by time. And C gives us the rate we're moving in the z direction. So in vector form, this would be written as say if we had some initial position vector. So r naught is going to be x naught I hat plus y naught j hat plus z naught k hat. So this is our initial position, so just coordinate. And if this went in the direction of vector v is equal to a I hat plus b j hat plus c k hat this would have the parametric equation. Position vector r as a function of time is going to be our initial position vector, r naught, plus vector v times time. All right, so that's the same thing here. So if you were to write this down in its components, right, it would be x naught plus at I hat plus y naught plus bt j hat plus z naught plus ct k hat. So next we're going to try an example with this. So this r, just keep in mind, is the line through the point with the position vector. So this is the line through the point with, so think of it as the starting point and a line going through that starting point. And then we have the direction. So let's try out an example. So we'll have a curve defined by the position vector or the parameterized curve. R is equal to minus 5 plus 3t I hat plus 1 plus 6t j hat, with 0 is less than or equal to time is less than or equal to 1, minus 6 is less than or equal to x is less than or equal to 1, and minus 3 is less than or equal to y is less than or equal to 8. And this is going to be a line segment because we have a start point and an end point for y. So looking at this, we have to figure out, let's look at the start and end point of our line segment. Okay, so we know it's a segment because we have limitations on time. So to find the starting point, what we're going to do is we're going to plug in 0 for time. Okay, so minus 5 plus 0 I hat gives us minus 5 for our x coordinate. And 1 plus 0 j hat gives us 1 for our y coordinate. So this line segment begins at point minus 5, 1, which you can see here, just like our example, right? We would have x naught plus at I hat plus y naught plus bt j hat. So this would be our x naught, y naught. Okay, so minus 5, 1. And it's going to end, so we have to figure out where the line segment ends, we have to plug in 1 for time. That's the end of our time interval. And so we have minus 5 plus 3 for our x component, which is going to be minus 2. And we have 1 plus 6 for our y component, which is going to be 7. Okay, so from a time of 0 to 1, this parametric curve is the line segment that starts at minus 5, 1 and ends at minus 2, 7. So now let's consider the line that passes through the points 1, 7 and 4, 1. And let's give a parameterization for that. All right, so we're going to start, in order to do this, we have to mark a starting point and an end point. So let's start at 1, 7. Okay, so that's our starting point. And so we need to think about how to get in the x from 1 to 4. And so in order to get from 1 to 4 in the x direction, we're going to have to move 3 I hat to get from 1 to 4. And then to get from 7 to 1 in the y direction, we have to move minus 6 j hat. So this is going to be the direction vector, this v. Remember, and our position vector is going to be our starting point. So that's 1 I hat plus 7 j hat. So that would be our starting point. And so remember, when you write out a parameterization for a curve, it's going to be this r of t naught, this vector r naught plus vt. So let's do this. So it's going to be 1 plus 3t I hat plus 7 minus 6t j hat. Okay, so it passes through 1, 7 and along the vector 3I hat minus 6j hat. For part C, if a particle is traveling along this line that we came up with in B, where is it at time t equals 2? So in order to figure out where the particle is at time t equals 2, we just need to find r of 2. So we plug in 2 for t. And so we do 1 plus 3 times 2. So 3 times 2 is 6, plus 1 is 7. So our x-coordinate is going to be 7. And our y-coordinate is going to be 7 minus 6 times 2. So 7 minus 12 is minus 5. So we're going to be at 7 and minus 5. Part D, give a parameterization for a line parallel to our line from B that passes through 5, 2. All right, so in order to be parallel, it has to have the same vector v. So it has to have the same direction vector, but it's going to have a different starting point or line that it's, or point that it's passing through, point that the line passes through. So it's going to be r of t, and we want to pass through 5 for our x coordinate. And v is going to stay the same, so it's going to be 5 plus 3t I hat plus, so then we're going to have pass through 2 for our y coordinate, and minus 6t is going to remain the same. So that's all there is to that piece. Next, give a parameterization for the line segment that begins at 1, 7 and ends at 4, 1. Okay, so for this one, what we can do is, well, let's go ahead and use our parameterization from B. Okay, so starting at 1, 7. Okay, so r of t is 1 plus 3t I hat plus 7 minus 6t j hat. But here's the thing. This would be, so to begin at 1, 7, that's time t equals 0. So if you plug in 0 for t, we have 1, 7. So the important thing here is the time interval when dealing with a line segment. And then we have to come up with an end time that brings us to 4, 1, like up above. So in order to get to 4, 1, you need t to be 1. Okay, so if you plug in 1 for t, you have 1 plus 3 is 4. 7 minus 6 gives us 1, 4, 1. Okay. How about the line segment that begins at 1, 7, 5, so looking in 3 space, and ends at 4, 1, 5? Well, we can use close to the same parameterization as far as, because here our x and y coordinates are remaining the same. So 1 plus 3t I hat plus 7 minus 6t j hat. Okay, but here's the thing. There is still a z component here. And the nice thing here is z remains constant in time, so it's not moving. So our direction vector is going to be 0 k hat for that. So we just have 5 k hat. That just remains constant throughout. And it's still through the same time interval. 0 is less than or equal to t is less than or equal to 1. Now we're going to get slightly more physicsy with this next exercise. And we're going to consider, this is number 67 from your book, we're going to consider two particles traveling through space. At time t, the first particle is at the point minus 1 plus t for the x, 4 minus t for the y, and minus 1 plus 2t for the z. The second particle is at minus 7 plus 2t for the x, minus 6 plus 2t for the y, and minus 1 plus t for the z. So let's describe. So first, we have a line segment. I don't know how I just zoomed. Give me 1 second. There we go. So first, we have a line segment. So the first line goes through the point minus 1, 4, minus 1, and is parallel to the vector. So we look at the coefficients for t here to get the direction vector. And it's parallel to I hat. Okay, so that's just 1t, minus j hat, since that's minus 1t, plus 2k hat, since that's 2t. And the second line passes through point minus 7, minus 6, and minus 1, and it's parallel to 2i hat plus 2j hat plus k hat. Now, we have to figure out whether the two particles collide. And then if the particles do collide, when and where. So in order for the particles to collide, we need the following. We need minus 1 plus t is equal to minus 7 plus 2t. So we need these x components to be equal. And so then we can go ahead and solve for the time at which those x components match up. So it'll pass through the same x at time t equals 6. So because here we have 2t minus t, so that's t is equal to 6. Okay. Minus 1 plus 7. And so that's our x component, but then we need the y's to match. So for the y's to match, we would need 4 minus t is equal to minus 6 plus 2t. And so this will give us t is equal to 10/3. And then finally, for the z components to match up, so we need that to match, and minus 1 plus 2t is equal to minus 1 plus t. And this gives us t equal to 0. So the thing is, this particle, these two lines or these two paths that the particle travels, they do not have the same coordinates at the same time. In order for the x coordinates to match, that's going to be at time t equals 6. For the y coordinates to match, it's going to be at time t equals 10/3. And for the z coordinates to match, it's going to be a time at t equals 0. So no, the particles do not collide. In order for them to collide, t would have to be the same throughout. We'd have to have the same t. So now let's figure out whether the paths of the two particles cross, and if so, where. So let's set up some equations here. So for x, we have -1 plus some time 1 is equal to -7 plus some other time. Because we're trying to figure out a time at which, or a place at which these particles cross. And we can figure out the place if we solve for time. So t1 is going to equal -6 plus 2t2. And we also need for y, we have -4 minus t1 is equal to -6 plus 2t2. So what we're doing here is we're trying to find a time for the first particle and a time for the second particle that would give us, they're going to be at the same coordinates if their path crosses, but at different times. So we have to find a time for each at which they're at matching coordinates. All right, so for this, let's just solve for t1 and for t1 in terms of t2 once again. So this will give us 4 minus -6 plus 2t2 is equal to -6 plus 2t2. So I'm just subbing in t2 for t1 here so we can solve for t2. Okay, two unknowns, two equations. So this is going to be 10 minus 2t2 is equal to -6 plus 2t2. So 16 is equal to 4t2. So that tells us t2 is 4. And so the for x and y coordinates to match, t1 would need to be -6 plus 2 times 4, which is 2. So at time t1 equals 2, the first particle is going to be at -1 plus 2 times 2 is equal to 3. So this will be giving us our z coordinate. So that's going to be, to get our z coordinate, it's going to be at -1 plus 2 times 2. This is for z. And for t2, for the second particle, we need to figure out the z coordinate. For t2 equals 4 to give us our z. And that is going to be -1 plus 4 is equal to 3. Okay, so we do have the same z coordinates when we have matching x and y coordinates. So that means that yes, these paths do cross, at point 1, 2, 3. Because if we plug in 2 for t1, that gives us -1 plus 2 is 1 for our x, and 4 minus 2 is 2 for our y, and we figured out 3 is our z, and if we did t2 equals 4 for our y, we have -7 plus 8 is 1, and we have -6 plus 2 times 4 is 2, and then we have 3 for z. So the paths do cross because they have a matching coordinate in there, and they cross though at different times. Okay, well, that is it for this lecture. And next time we are going to get a little more into physics, looking at velocity and acceleration vectors. So I will see you next time. Take care.